I'm recording the class now. So let me just get my screen up for the whiteboard. Actually, before I start, any comments? I'm assuming that you guys see my posts more than likely you do, but I just made a post last night indicating that on CK12, you have to click you have to mark it done. Otherwise, when I pull up the report, it essentially shows it like you never did anything, which could be true, but for some people it wasn't true. And I had to mark it done for you, which is fine because I didn't even know I could do that. So I learned that piece. But just moving forward, when you do get CK12 assignments, be aware of the marked done. So, again, I am able to, because I didn't know. Again, this is new to me, and some of you didn't know either. That's fine. Um, but just realize that if you didn't mark it done, when I pull up the report, it just essentially shows 0%. Even if it was 99% done and you didn't mark it done, then my report says 0% done. So that's for that reason, students got zeros, but then they emailed me and I fixed it. So just be aware of that. And it's not to say that every assignment is going to be in CK12, not by any stretch of the imagination. But we will use it when I feel like it might be useful. Okay, I'm now going to share my screen. I'm going to then describe vector addition. And I am going to go through it relatively quickly, meaning I'm not going to fly through it. I'm just going to do what I have to do. But the point is, I can't go into the detail. I can't go into the detail of all the sign is opposite over this and like all that detail that I provide before. It's to expose the student to be like, oh yeah, I need to know this stuff. Once we're moving through the year, I can't do that kind of detail all the time. So again, if you feel like you're struggling somewhat, if you do with the trig, then you need to reach out to me so I can maybe see what I can do to help you practice the trig that you might need. Okay. And then after I do this, I'm going to give you one to work on your own. And it just takes a while, and you might say, boy, it's taking a while. And I think it's that important. I think it's really important for students to understand the trig and the geometry. Again, I don't want you to think that all of those things I just mentioned are involved in every unit, but they're involved in a lot of the units. All of motion will involve vectors, the unit of motion. All of Newton's laws will involve vectors. Technically Newton's third law. I guess you could argue that it's vectors. You push on something forward, it pushes back on you. Those are vectors. So then when we get into momentum, it's all vectors, vector-based. And other units that we use are not necessarily vector-based, but like what I've described is already a huge amount of the curriculum. So for that reason, I'm doing this because, again, it takes, even though doing a vector addition problem, they would never say, here's two vectors on an AP exam. Calculate the magnitude of the resultant vector and the direction of the resultant vector. They're never going to do that. They will give you vector-based problems and ask you to make drawings. They might ask some pretty hard conceptual questions relating to geometry and trig as it relates to a physics topic. But again, I'm only doing it because I have enough knowledge to know that if a student, or if any human being can do a vector addition correctly, then they know their stuff. They have it down. So that's why I'm doing it, because I know it'll be a good assessment tool. And further develop your understanding of those things. All right, so let's just dive in. In fact, before I do this, why don't I at least just let you visually see it? That makes the most sense, I suppose. And I already had it open. I'm not sure I have multiple windows going right now. Where is it? There it is. Should also be sure I am recording. I'm supposed to technically do captions. So I guess I'll do captions. 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 Let's see them. Hello? Caption. Where are you? My mic working? Hello? You guys hear me, right?
Yeah.
You wouldn't have let me go this long and finally tell me that you didn't hear me, right? Okay, good thing. All right, maybe I should have always asked that. I don't know. Oh, they're the captions. Now I see them. All right. So what we're doing is we're looking at vectors. We now have an understanding of components, that each vector has a horizontal component and what's called a vertical component. If this was vector A, then this would be referenced as AX, and X would be small. It's called a subscript. This would be AY, to indicate it's a vertical along parallel to the y-axis. AX to indicate it's parallel to the x-axis. They have certain directions, right? That's the angle in here. And we know how to work out the physical length of each of them and the directions as well. Because remember that it doesn't have to be a first quadrant vector like this is. It could be a third quadrant vector like this is. And you now have to think about reference angles, potentially. You have to think about the full direction, the reference angle. You have to think about the directions of the actual components, left or down. You need to know how to make them either positive or negative. If you're using the reference angle, you have to be aware of that. If you're just sticking the full angle in, you don't. And then that's all the things we've already reviewed. And then you have to add them. So let's just say I removed this view and said, and I'm not going to do two first quadrant vectors. I'm going to make it harder. Let's say that these are our two vectors. In fact, I'm going to make this one a little different. In fact, how should I do it? Let's do it like that. Why they call them both V, I have no idea. I mean, I don't care what you call it. Just call them something different. They shouldn't be the same thing. They're two different vectors. They should have two different names. So that's a little bit confusing. So let's just get over that. I'll call this vector A, and I'll call this vector B. So if we're adding vector A to vector B, again, you're doing the head to tail method. We've talked about that quite a bit. And then the resultant is the answer to this vector addition problem. Adding vectors means you have to place, again, the head of one vector to the tail of the other vector. So this is the head of blue vector touching the tail of orange vector. Maybe that's what I'll call them. This will be not A vector. It'll just be blue vector. This will be orange vector. They have to touch head to tail. This is equivalent, again, to saying what is 7 plus 3. In numbers, it's 10. In this case, we're saying what is blue vector plus orange vector. It creates a new number, just like 7 plus 3 creates a new number, the number 10. That new vector is called the resultant vector. And it's a vector that points. Why is it? What's going on here? That's not correct. Maybe I'm not very sure what's going on. Sorry, give me a minute. What the heck? What is happening here? That's not correct. So the resultant vector should be going this way, from here to here. So that's not, why is it not giving me? Okay. Well, I never used the lab before. I guess I'll get away from the lab. There's many choices here, and I chose lab. I'm not sure why. Maybe just different then. Let's try this one. Nope, there's vector A. They've labeled it as vector A and vector B. All right, they're both blue, so now we're back to A and B. So let's say this is vector A and this is vector B. Let's make this one a little longer. Increase its magnitude. Okay, and so now when I hit the sum, there it is. This is now called the resultant vector. It's the answer to the question. But to describe the answer to the question, you have to be able to describe the properties of this resultant vector. And it only has two properties. It has a length, which is called the magnitude of this vector, and it has a direction, which could be any direction between 0 and 360 degrees. And again, when I move it over here, we can see that this is now vector A plus vector B equals vector S. Vector whatever, you call it vector C, vector R for result, whatever, doesn't matter, as long as you physically understand that. So how do we work that out? Again, this is referred to as determining the magnitude and direction of the resultant vector. Where in this case, we're doing vector A plus vector B equals, usually it would be called C. They called it vector S, but let's just call it, makes sense. AB, well, why not C? So vector A plus vector B equals vector C. Vector A plus vector B equals vector C. And the resultant vector is this. Okay, so how are we going to do that? So what we're going to do is we're going to look at both of the vectors separately. Let's look at vector A. Vector A looks like this. And it has some components. The components are right here and right here. This would be considered the Y component. It's a Y. And this would be the X component. And it has some direction. I'm going to label it theta A to indicate that it's the direction of vector A. Capital A, whatever, lowercase, doesn't matter. I have to give these things some directions. So let's do that. The direction of vector A, just based on what I can see, remembering that this is kind of the 0 degree, so 45 degrees. So let's say this is a 45 degree direction for vector A. And then I have to give it some length, the magnitude of vector A. Tell me what number you like. Give me a number. Anybody tell me your favorite number?
12.
All right, we'll go with 12, Matt. It's going to be 12. We're going to make this a displacement problem. Why not? Let's call it miles. So if we were back to this being a displacement problem, which, like, why not? I mean, why not make it a physics application, which is one of the first topics you have to tackle. Again, this would indicate that you are potentially walking in the woods, like this is your starting spot, where you parked your car, let's say. I mean, I guess I could. It just takes time. I mean, I could pull up a map, but I think just verbally saying it to you is sufficient. I mean, that's what I originally had that first day, having a map, and then I can draw these on the map. So students like, yeah, I get it. You know, we're in the woods and we're showing that somebody walked from their car to here, and it's a perfectly straight line, which nobody ever does, but in this scenario they did. Although it really doesn't matter because this is a displacement vector actually, right? Because they could have really went and then stopped here for lunch. If someone said they went along that weird path, draw the displacement vector between those 2 points, straight line. So I suppose it doesn't necessarily mean that they actually walked along that perfectly straight line. But if they did, it would be the same thing. And then they decided to change their heading. In navigation, we call it the direction of motion in terms of an angle. In reference to a compass, we call that the heading. Planes, boats certainly use that word, heading. What's your heading? So I'll use it. They changed their heading, and now they head in this direction, which looks like it's a southeasterly direction because they're traveling down as well as to the right, which is east-southeast. Not exactly southeast, because southeast means just as much eastward as there is southward motion. That's a 45-degree angle and heading in the downward fourth quadrant. You can't say anything that's down and to the right is southeast. You'd say southeasterly. If you want to be specific, you got to give me the exact angle. If you actually say southeast, that means that it's literally 315 degrees, perfectly in between 270 and 360. So they changed their direction of motion. They end here. And now again, maybe they break their legs, they fall, they hurt themselves, and then somebody needs to come find them. I like to use this example because it seems to make sense. So the helicopter arrives at their car, and then the helicopter wants to fly in a perfectly straight line from the car to go find them. And now they look down and hopefully see the person, and they lower somebody down, they rescue the person. But in order for the helicopter to do that, if they started at the car area, they would need to know the resultant vector, right? They would, because that's what they'd fly along. They're not going to fly along some crazy path. They know the direction to go and the distance to go. It's the straightest line between the 2 points that will get you there fastest, and that's what you would do. So they would fly along this, right? Or if this person wanted to walk home, right? You can think about that. Maybe they didn't hurt themselves. They went here to here, and then now they're here and they want to get back to their car. Straightest distance would be this also, but just the other direction, the negative of this vector. That's useful too, right? So that's me just kind of putting it into a story or into a physics application. Let's get back to, before I do that, I just want to make sure. I did click record, right? Yeah, I did click record. Okay. Okay, so here we are back here. So we're going to say that vector A was 12 miles. Now let's get some information for vector B. I mean, you could put a little vector symbol if you want there. It doesn't really matter. So let's see. What does this direction look like for this vector here? If it's heading kind of like that, I didn't do that perfectly, but it doesn't have to be perfect. We know straight down is 270 degrees. So I don't know. Doesn't look like the way I drew it was quite on the 45. Maybe a little less. So let's say it's 30. Let's say it's 30 degrees. So let's call it 300 degrees. And now what we're going to do is decide what is the length of this vector, vector B. Well, just based on how I drew it, it's definitely longer than vector A. And we have to reference Matt's number 12 and say, all right, well, if that was vector A and, this is like this, vector A is about the same distance from there to there. I'm not doing it perfectly. Yeah, kind of looks like double. Let's go for it. Okay. Now let's erase some of this unnecessary stuff. Okay, so you'd always start with visualizing each vector on its own, like I've done here, vector A. I might even recommend, think now. Ultimately, I'm going to work out the signs of these components. What are they? Are they plus or are they minus? This is up, so maybe just a little indicator for yourself, just to remind yourself. You're going to have to remember that. And this one would be plus 2 because it's to the right. And then we're going to now work out the components, AX and AY. AX will be the magnitude of A, cos theta, as long as we have used the reference angle as recommended by Mr. Kurtizak, which is drawn from the vector back to the closest approach of the x-axis, which I have done. All right. This was 12 cos of 45 degrees. Now, I know cos of 45 is 1 over root 2, and so should you. If you don't, it's okay, but just warning you now that this is going to be stuff that you do need to know. Again, that comes from the 45-45 special triangle, 45-45-90. And then the definition of cosine, which is what we have here, is adjacent over opposite. I didn't mean that. Adjacent over hypotenuse. So if you chose this one, adjacent is 1 over hypotenuse, which is root 2. Or if you chose this one, adjacent is 1 over root 2. So no matter what you do, it's 1 over root 2. So I'm getting 12 over root 2. I don't know what that is. To be honest, I don't really care right now. I just know that it's 12 over root 2. And I'm going to call that miles. It's a physical distance. We can turn it into a number. In fact, maybe I do care. Let's turn it into the number now. Why not? 12 divided by root 2. And I do encourage you to follow along with a calculator, because there's calculator skills too that, I want you to have. And even though, you're not necessarily going to be using a calculator very much during the AP exam, you might ask yourself, and you should, and so have I, am I really just teaching these kids for this AP exam? Am I just entirely teaching to the test? If so, shame on me, because there's a lot of physics that you will need to know when you are ready to head into college if you're interested in science or engineering or any STEM topic. And you should learn that in an AP class, right? Just because it's not on the AP exam doesn't mean you shouldn't learn it. So my point is, I'm going to have to balance that. I'm going to have to balance the judgment call as a teacher of how much do I teach to the test and how much do I teach to prepare them for college. There'll have to be a mixture of both, in my opinion. And there certainly are teachers that do not. They just teach to the test. That's all they care about. I've known them in the past, and I don't agree with it philosophically. Whole purpose of this is just to potentially start yourselves in a STEM path so that you're ready if you go to college to deal with some of this stuff. So your head's not spinning like a lot of people's heads are doing when they enter college and see this stuff. And like, I've never seen this stuff before. And the professors are just flying through it. You know all this already. You're like, no, I don't know all this already. Well, I'm preparing you for college too. All right, so I'm pointing out, I recommend that you take out your calculator and work it out. 12 over root 2, I'm getting as approximately 8.49 miles. Okay, that's the X component. And then I'll connect it with my picture and say, all right, it's 8.49 miles. Right here, just to add it to my little visual that I have here. Now I'm going to work out the Y component. The only difference for the Y component is that I use sine instead of cosine. As long as you've taken my recommendation to draw the angle back to the x-axis, then you can always feel comfortable doing that. No, it'll be right. Sine of 45, we have our picture here. Again, store it to memory if you haven't already. Sine is opposite over hypotenuse. Store that to memory if you haven't already. Pick an angle like 45. Opposite would be 1 divided by hypotenuse, which is root 2. Or if I pick this 45-degree angle, opposite would be 1 divided by hypotenuse over root 2. Oh, so sine of 45 and cosine of 45 are both 1 over root 2? Yes. Yes, they are. Because if this was your 45-degree angle right here, then if the length of this is 1, the length of the hypotenuse is 1, then how long is this one? 1 over root 2. It has to be smaller than 1, so you have to divide it by a number that's greater than 1. Root 2 is a number greater than 1, right? How long is the vertical piece in this 45-45 triangle? It's 1 over root 2. Because they're equal. It's a 45-45 triangle. Both legs have to be equal. This is the reason we're getting this result. The same. Because I made that choice. Now I'm going to tell you, I went through those steps, but it becomes critical that students in an exam can pick up on those things quick to save time. Because time is of the essence during an AP exam. And whether you finish the exam or not, like physically finish it. Some people do, some people don't, for sure. Depends on how good you are at collecting those minutes where you can save a minute here, save a minute there, save a minute here or there. Those become important. So a student in this example saying, wait a minute, this is a 45-45 triangle. If I've worked out whatever the X component is, I already know the Y component is that. Move on. You don't want to spend a minute thinking about all this stuff like I did and writing it all out. You're just already wasting too much time. You have to be able to pick up on those things if you want to get through the exam, and it's just my recommendation. All right, so I have those. I'll just maybe jot them down over here just so I have reference to them. So when I erase this board, which actually, yeah, it's fine. I'll do that. This is 8.49 miles, and so is AY. Okay, and so I'm going to erase. And now, erase. And now we're going to look at vector B. Vector B is not a first quadrant vector. You can think to yourself, what quadrant is it? Just look at the picture I've drawn on the left of the screen. What quadrant is vector B pointing in. That's a third quadrant. I'm sorry, that's a fourth quadrant vector, right? Because fourth quadrant is over here and it's pointing this way. So I did that on purpose because I wanted you to have some exposure to the possibility that some of these components might have to be negative, and you have to think about that. So let's just make our little picture. Let's look at vector B by itself. All right, so let's draw in the components. Don't do that. Don't do it. Draw your X first. Draw your Y next. Because if you did it the other way, you're going to potentially switch sine and cosine up, and many students do. My recommendation, again, is to have an angle that you're using that goes back to the closest x-axis. We talked about that already. What was the direction of this? It was 300 degrees. We know in the downward direction was 270 degrees. That tells me that this amount is 30 degrees. That tells me that this amount must be 60 degrees. Right? Because all the way around the whole thing is 360 degrees. So if we know that this amount is 300, well, this must be 60. That's the angle that I'm going to use. That's my choice. Oops. Let me just erase some of that. Actually, I'll just erase all of it because it gets too messy. But at least you understand my thinking. That's a reference angle. Not usually thought of as negative. It's usually, I mean, if you were showing the rotation down, then yeah, you'd say negative 60 degrees. In my experience, reference angles are usually just the angular separation between two lines, which is not directional. So it's just 60 degrees. Okay, so we know that this is an x component. So we know that, we're not doing vector A. Doing vector B. We know that Bx is going to be the magnitude of vector B cos theta, and that By is going to be the magnitude of B sine theta. Maybe take a look at the components just to remind yourself. This one is down. The vertical one is down. So think, that's going to have to be a negative. And then I'll talk about that in a minute. Because if you decide to insert that negative, then you can only use the reference angle. If you insert this negative manually and you use the whole entire angle like this and you put it into your calculator with the angle of 300 degrees, then you're going to get a minus from doing the 300 in the calculator, another minus that you manually stuck here, and you're going to end up with a positive. So I say avoid all that confusion. Just look at it. Just look at it and think about it. That's just my recommendation. It's your call. The x component, on the other hand, is to the right, so that's going to be positive. All right, what is the length of B, the magnitude of B? 24 miles. And the angle of vector B. Again, I have 300 degrees. Personally, when I like doing these kinds of things, I'd rather put the 60 in because that's my reference angle. That's just how I am. If you wanted to put the 300 degrees in, you certainly may. You'll get the same results because you can do that, right? You can say, what is 20 on a calculator? 24 cos 60, enter. And then do 24 cos 300, enter. It gives you 12 in both cases. But when it's not in the first quadrant, when it happens to be in other quadrants, sometimes the signs do get messed up. All right, so let's just do that. I get 12, right? And I just did it, 12. MI is usually the short for miles. For the y component, it's going to be negative negative 12 sine of 60. And again, there's a triangle for that, right? There's a triangle for that. Like there's an app for that. Like there's a triangle for that. This is an important one to know. Sine of 60. Here's your 60-degree angle. 1, 2, root 3. 2 goes with the longest piece, the hypotenuse. 1 goes with the shortest piece because it's the smallest number. 2 is the biggest number, it goes with the longest piece. The other one must be root 3. So if I'm looking at sine of 60, Sine is opposite over hypotenuse. Find this 60-degree angle. Opposite is root 3 divided by hypotenuse is 2. So I know that this, in a physics exam, if they happen to represent this as, an exact answer, I'd be potentially looking for that, but they'd even be, more specific. They would write this. Because that's how they are, right? Like they're going to test all of your abilities. So be aware of that. What is 6 root 3? I don't know, but I know it's 6 root 3 because 12 over 2 is 6 times root 3. So let's do 6 root 3 on the calculator. 6 root 3, enter, 10.39. Negative. Don't forget about your negative. If you're doing it my way, it's up to you. Why should it be negative? Because he was moving downwards. He was heading south, right? During trip A, he's moving north. And then during trip B, he's moving south. If those were both the same sign, then they would add up to become one larger number, which that can't be. It doesn't make sense. In the first trip, he's moving up. The second trip, he's moving down in terms of the vertical axis. Those must be different signs because the only difference that really matters is the difference from here to here, right? This part going up and this part going down are going to cancel, right? And the only remaining bit that matters is right there. Okay, so we have by. That's going to be later. What I just mentioned later is when we add them. But anyways, let's just stick with this. We have all of our numbers. We have everything written out. I have everything written out. So now what we're going to do is start listing everything out nice and neat. Any questions at this point, you feel free to ask at any point. But before I move on, are there any questions at this point? Here's vector A, here's vector B. Here's what I'm going to put as AX. Here's what, I didn't mean to say that. I didn't mean to write that. Here's what I'm going to put as the X component. This is what it's going to be, the row for the Y component. Let's make ourselves a nice, neat little chart. I know AX was 8.49. The units, you can put the units up here if you want. I'm not going to write them every time. Remember that was the first part of the trip when he was heading eastward while he walked along that hypotenuse. So that would have been plus. So this is a chance to make sure you have those signs correct. And I'm forewarning you now that this is, when students do get it wrong, most of the time, when we dig down into what they did, we're like, it was the sign. It was a sign that got you. A lot of times the math part is all good. Their cosines or sines or everything they've done. That wasn't supposed to be negative. That was supposed to be plus. So this is your chance to really look at that when you're doing this. The Y component I know had to be equal to AX because it was 45 degrees, right? So if this was 8.49, then this had to be 8.49 because it was a 45. That's messy, but it's a 45 degree. So 8.49 miles. Those were equal. This right here is really your net. This is the row where you're going to put the net result. Again, the net is just the extra amount in a certain direction. Like when we talk about net force, which we'll in the second unit, right? If someone says there's 5, newtons of force this way, and there's 7 newtons of force, and some object is feeling both of those forces at the same time. 5 newtons to the right, 7 newtons to the left. What is the net force? It's the extra amount in a certain direction. This 7 Newton vector is really 5 newtons plus another 2 newtons, right? 5 plus 2 gives you the full 7. What is this 5 newtons to the right plus this 5 newtons to the left? Nothing, they cancel. What is the resultant or the net of this? 2 newtons to the left, right? It's the extra amount in a certain direction. That's what net means. Okay, so we ultimately are interested in the net result. In this physical problem, we know that he walked vertically upward in part A of his trip, and then he walked downward in part B of his trip. We need to know what is the net amount. That's in the y direction. That's ultimately going to end up over here in the net row, but over here for, I didn't mean to say that. No, I didn't mean to say that. Oh, so sorry. Wow, I'm just catching this now. I made my chart wrong. So sorry. What did I do wrong? These are supposed to be the x's. Oh, I flipped it. Oh, geez. So sorry. Not that anything's wrong. I just set this chart. I set this chart up incorrectly. I'm sorry. Please forgive me. Been a full year since I've done this, I suppose. A little rusty. This is supposed to be this on this side, x component and y component, not on this side, but on top. And then your x, your A goes this way, your B goes here. Oop, yike. And then this is the net result, the net, which we'll call C, the resultant vector. And so the AX, all X components have to go in the same column because you're going to be adding those together. So I would put 8.49 here and another 8.49 here. Okay, and now when we move over to the AY was the Y component of, oops, I'm still making a mistake, so sorry. All right. AX, AY, those were the same. Now when we move over to BX, what was BX? I know the Y is on the bottom of my page. So BY, that would be here. What was my X? I erased it. Can someone tell me what was that? 12 cos 60. 12 cos 60, enter. Or no, B was 24. Take that back. 24 cos 60. 12. Okay. So this was 12. So I'm looking at two positive X and Y components for A, and a positive X for B, yet a negative Y component for B. So let's just make sure, let's just go back to our visual and put these in. Maybe not that one, maybe not that one. Particularly like either of those views. Yikes, I don't want that. Take away the sum. Like that one, there we go. That's the best view. So the A has two positive components, AX and AY. Trip B, when he's heading in the southeasterly direction, he has a positive X, yet a long Y component in the negative direction. And I can see that the longest component in all of this trip should be BY, right? It's the longest walk. The longest distance along a particular axis should be BY. And I can see that the shortest one, should probably be BX. And these would be equal if it was a 45-degree angle. So you can look back at the numbers, make sure that makes sense. X and Y are both positive. Maybe the numbers aren't exactly matching that because in my picture I made BX look like it was the shortest, yet it's not in this. But I was just kind of freehanding those vectors on that app. So yeah. So I mean, I take back exactly what I'm saying when you're comparing the two. It depends on how careful you are. I mean, there are some simulators that you can use that when you can actually plug in the information that you have here. And when it shows you the vectors on the screen, it's exact. And when you have a tool like that, then the numbers in your table should perfectly match the picture. But I was just like freehanding it when I was moving those vectors around and making them certain lengths. I was estimating that stuff. All right, so now we're going to add. And the reason we're going to add, so that's super duper clear, is because if we're looking for what full distance did this person walk horizontally, it's this distance plus this distance. That's the total eastward direction motion he had. We might call that the net x displacement. It's a displacement along the horizontal axis, so we call it x. And we'd say it's the net because we're really going to add this one plus this one, right? Because if I put the sum, the resultant vector here, which is right there, the x component of the resultant is equally as long as ax plus bx equals cx. So I'm now going to go back to my thing here to add those up. This is ax. This is bx. This is going to be cx. Let's add them. 8 and 12 makes 20. Throw another 0.49 in. So this is cx. That's the x component of the resultant vector. It's really east. So if you were having to tell a helicopter this, you'd say his final position is 20.49 miles to the east of his car where he started, which where he started was the beginning of vector A. Now we're going to look at the y components just to make sure that that makes sense. Because if you're not making sure it makes sense, then you're not doing physics. That means you're just doing math. But if you're stopping to make sure that it makes sense, that means you're doing physics. I mean, if it's a physics problem, this is a physics problem. You have to do that. Now, if we're looking at the y component, again, this is our resultant vector. So that's, I know it can be confusing when all these things are in there. This is the resultant vector. And now we're visualizing all of those components. So if I'm interested in the length of the y component for this answer, known as resultant, it's this long. Well, how long is that going to be? It's going to be this number, which is a positive value, and then you have to subtract this number. So if this was 5, let's just say, and this was minus 10, let's just say, then the extra amount, which is right here, the net y would be minus 5. Because if this was 5 and the y component on vector b was negative 10, then what's the leftover amount? Remember, this one would have canceled with the negative 5 heading down, and the leftover amount would be minus 5. And indeed, you'd say, well, 5 minus 10 is negative 5, right? And that makes sense because that would be then negative 5. So it's still true that ay plus by, even if it's the negative value, is equal to cy. Makes sense. So here we are looking at our chart. This is ay. This is by. Let's compute cy. 8.49. And again, my picture didn't perfectly match with our table. I already talked about that. Minus 10.39. Maybe I should find a sim that actually does that perfectly so it matches. I don't know if it matters. All right, 8.49 minus 10.39. If you're following along at home, you got negative 1.9 miles. So that means it's south of his initial position. You might call the initial position y initial. Y indicates it's a vertical position on a grid, and I indicates it's kind of too big. I mean, yi is usually, y, and then I is like that. So it's south of his initial vertical coordinate, because this is a coordinates, right? This is a coordinate system, right? So he had originally a position on a map, and you'd have to figure out what the position of that car was, but it's certainly in our latitude and longitude of a globe. It's a number, an angular number. For us, for example, I think we are 41 degrees latitude. Longitude, I don't remember what our longitude is. But anyways, everything has a position on this global grid. It's called latitude, lat long is short for latitude, longitude. And then again, if you're referencing these things, this is technically a coordinate, right? If you're a math teacher, you're going to call it an ordered pair, right? You're going to say, all right, his final position in the in the grid that we're referring to would be 20.49 comma negative 1.9. You'd have to say, where's 0, 0? And in my case, you'd say, well, 0, 0 is his car in the parking lot where he started. That's the origin, because that's where his trip started. So the car in the parking lot, which is really over here, this would be your 0, 0. And if this is an ordered pair, this means the helicopter has to fly 20.49 miles eastward, but this arrow would actually be up here. And then he's going to go down by negative 1.9 miles, which again, doesn't look very good compared to my picture. But again, it's just because I don't think I was doing a good job with drawing. At least that's my hope. If there was any errors, I hope you would speak up. We've talked about that before. I don't think there are, though. I think it's correct. Okay, so now when you have that information, I'm going to erase this part. Now you can work out how long the resultant vector actually is, because currently all we know are the x components and the y components of the resultant vector. And in our picture, we know that the resultant vector has a lot of y component to it, because I can see this. Oops, saying that backwards. Sorry. Our resultant vector has a lot of x component to it, because this was 20.49 miles. Remember, this is cx right here, 20.49. And then cy was down just a little bit, south just a little bit by a couple miles. What's in miles? So the resultant vector would technically be something like this. And I still can't quite, I mean, it's making me, why is it so small? Is there a mistake in here? I hope there's not. I feel like it should be, y component should be larger. Hopefully I was in the right mode. Yeah, I'm in degree mode. Just give me 1 second. 12. Just want to check something, because if something doesn't seem right in physics, then you got to check. Confirm 8.48. Check that checks out. And then we had 4 cos. My original angle was 300 degrees, so 60 makes sense. 12. Can somebody confirm that I had 12 in for the C? I'm sorry, 12 in for the x component of vector B by looking at the chart. Was that 12?
Yeah.
Okay,
Yeah.
that's correct. So then 24 sine 60, 20.78. That would have been the y component of vector B. It would have to be negative. So can someone confirm that the y component of vector B was 20.78? Anybody? Did I make a mistake there? Was it 20.78?
For the y component of
vector B.
Of vector B,
Yeah.
I got negative 10.39.
I did make a mistake. How am I making a mistake there? What am I doing? How did you get? I'm getting, so if I did 24 for BY, it should be magnitude of B sine of the angle. And magnitude of B was 24. And I very well could make a mistake, because this just doesn't seem right to me. This just looks too tiny to me. So maybe I'm going to finally figure out why. Sine, this would be 60, right? 24 sine 60. I get 20.78, but it would be negative because it was down. Oh my God, 300, did I make a mistake with, no, I didn't. I didn't make a mistake. 300 degrees is fourth quadrant. So how did you get that, Matt? How did you get 10 point, whatever you got? Didn't I write, did I write 20.7 in my chart?
No, I think you did 12 times the sine of 50.
Oh, I did?
Yeah.
Ouch. I put 12 in there. I'm so sorry. So when you see that, please speak up. 12 times the sine of 60 instead of 24. 10.39. Is that the number I had in there? 10.39, Matt?
Yeah, it was.
Shoot. All right. Well, not the end of the world. Not the end of the world. Not the end of the world. It's never the end of the world. Give me a moment. I will try to fix this. So sorry. But at least it's an example of thinking about it, looking at the picture. I knew that y component is just, there's no way it was that tiny. It's a good example of why it's useful to really look at what we have. So I know my, I'm going to just do this one more time, relatively quick, y component. And then I had vector A here and vector B here. These were definitely 8.49. If I make a mistake, just say, stop, you made a mistake. Bx, again, would have been 24 cos 60, which is 12. And then by would have been 24 sine 60, which apparently this was my error. This should have been 20.78, and it should be negative. Can anybody confirm that seems right to them? Anybody else do that? See that? Should be. And that would make sense because now when you add these, this number is not going to be so tiny here. So it's 8.49 minus 20.78. This number is negative. Thank you. That sounds correct. And it looks more like my picture that I had on the computer. Negative 12.29 miles. It's better. This is now CY. And now here we're going to put our CX. This is again the row for vector C. And that one was correct, 20.49. Much better. Thank you for your patience. Okay, so now that we have that, you're nearing the end. There's only like another minute left for a problem like this. A couple minutes. You would want to draw them. If CX, which this is positive because it's to the right, then draw it positive and to the right. This is CX. And maybe label it 20.49 miles. And then CY was, I don't know, a little longer than half of that. Maybe something like that. This makes me feel good. It just feels right in my bones. So that means the resultant vector, the one that the helicopter would fly along, is this vector I just drew here. So let's call it C if you want. So how will we figure out the length of that? In that case, you can just use Pythagorean theorem. It only takes a minute. So you'd say C squared in magnitude is equal to A squared plus B squared. That is Pythagorean theorem. So let's see, what do we have? You'd do 20.49 squared plus negative 12.29 squared. So I have to do that out on a calculator. 20.49 squared plus 12.29. Doesn't really matter if you put the negative in there because you're squaring it, right? Negative number squared is still positive, so you just ignore it. It's up to you, whatever. So then you plug those in, hit enter. I essentially am getting the magnitude, the length of this, which is called the magnitude of C. I'm getting, when that length is squared, we get the number 432.13. But of course, I have no interest in that distance squared. That's completely useless. Helicopter's asking how far to go. You tell him it's the distance between him and the person squared. He's not going to be very happy. So I have to square root that. Square root of 432.13, enter. Of course, this is just a square root. So C in magnitude as a vector, if you want to put the vector symbol there, go for it, is approximately, and I should put the approximate symbol, 20.79, because I like to round typically to 2 decimals, and that's sufficient for what we do. Okay, so that's the length. That's the physical length. And this was his car, right? And then he walked way up like this, and then he came way down like this. And this is where he got injured maybe, right? So this is the straight line distance between where he started and where the trip ended. It's a straight line distance between the two. It's called the displacement vector. So I'm going to point out that in physics, we usually would call that magnitude of d with a symbol over it, d for displacement. And I'll point out that these, instead of calling them c, this usually would be called little lowercase d net in the x, because that's the sum of your x horizontal motions. And in a textbook, they would show this as d net in the y, because it's the summation, the sum of the vertical motions. So that's me just going from math, ABC, to physics symbols for a displacement problem. You usually use lowercase for the x and y components. You use the word net to indicate that you've added the x components up to get that, and you've added the y components up to get that. And then when you're expressing the magnitude of d, it's usually a capital. The very last step. Because now if you told the helicopter who's floating over here saying which way to go, you'd say drive or fly 20.79 miles. He'll say, fine, tell me which direction to go. What is the heading? So now to find the direction, you'd have to figure out what this angle is. It's a reference angle for what we're calling vector C, if that's what we were calling it. That's a reference angle, right? So now I'd think, all right, what tool should we use? Sine, cosine, sine, sine, cosine, or tangent when looking at that triangle. I'm looking at this triangle right here. Well, I already have, if this is the angle I'm interested in, which it is, and I have what's called the adjacent piece here, and I have what's considered the opposite piece over here, because I know those numbers. I have this one and I have this one. Then I think, well, what goes with opposite and adjacent? Only tangent does. Tangent of theta c, which is really a reference angle. I can maybe just note that what I'm solving for, this theta here, is really, it's a reference angle. In the end, I'm going to have to think about the full angle all the way around, but it's the very last step. The reference angle is now opposite over adjacent. Opposite would have been negative 12.29. This is opposite divided by adjacent, which is this piece here to the right, 20.49. Notice that this would be miles and this would also be miles, so these would cancel, indicating that an angle is actually a unitless thing, a unitless quantity. So now we get to finish. Yep, that's a lot. You want to do well this year with anything that's relating to physics that has to do with vectors, you got to know this stuff pretty well. It just has to be zipped out. So now I'm saying, all right, I know that the tangent of this reference angle that I'm interested in for the resultant vector C is equal to this ratio, negative 12.29 divided by 20.49. And so therefore, to actually figure out what this angle is, I have to do what's called the inverse tan. Let's use this function backwards. Inverse tan of, all right, messy. Inverse tan of negative 12.29 divided by 20.49. You have to go to a calculator, make sure you're in degree mode, hit mode, make sure it says degrees. Where it says radian or degree, the black box has to be over degrees, assuming that you have one. If you don't have one, I would highly recommend you get one. It will be used this year. If you do, again, I would buy it on Amazon used edition. Up to you. So I hit second tan. Second is the yellow button, then tan, in order to access the inverse tan. And now it says, all right, what's your ratio? Negative 12.29 divided by 20.49, close parentheses, enter. My calculator is giving me an answer of negative 30.95 degrees. So in my last final thing, and then I'm done. You don't want to report the direction of that vector, that final resultant vector, in that format. You really don't. And even on an AP exam, they would not want that. Even if it's a AP math exam, they would not want that. Although I don't know if you guys do vectors in AP math. I'm not sure. I don't think you do. Anyways, the point is that the resultant vector, which we knew was like this, the negative value I just got right here, negative 30.95, is really this. And it's telling me it's negative because this part is directional. It's the computer's trying to say, hey, I want you to distinguish between this one and going up by 30.95. And the computer knows the language and says, I'll tell the user of this calculator it's negative, so they know it's fourth quadrant. Because up this way is a negative angle, down this way, up is a positive angle, clockwise is a negative angle. So then you just have to think, what's the total angle from here, which is 0 degrees, all the way around? Well, from here all the way around, like truly all the way around, I know it's 360 degrees. So I just have to back up by 30.95. So I would do 360 minus 30.95. I get a final angle, final direction. I can finally say I'm done with the problem. The final angle of vector C, the direction of vector C, is 329.05 degrees. It's technically an approximation. And then the magnitude of vector C, how long it is, was 20.79 miles. So if this was the real world, you would say to that helicopter who's hovering over the car, trying to find that person that's maybe injured at the end of that last vector, you'd say fly at a heading of 329.05 degrees, assuming that the 0 is at that car. You would then say fly a distance of 20.79 miles in a straight line in the direction or heading of 329.05 degrees, and then look down. You'll find them. Okay, now, yeah, it's a lot. It is significant, but it is what I want you to know how to do. I'm going to give you a problem, or ask if you have any questions first. Are there any questions? Because moving forward for the rest of the year, I'm not. I mean, I can again help you individually, but in class when we're doing things, I'm just doing it. If you have a quick question, of course I'll ask, but I can't always return to all of that because we just never get through the year. So if you have questions, it's important to ask. Do you have any questions at all? No problem if you have questions. Don't feel funny about asking questions. I lastly say, if you don't have questions, that there is a calculator that you can use. It's called a vector addition calculator. In vector addition calculator, enter. And I've used this one before. The second one, it's all capital letters. It says vector addition calculator. Click it. If you're checking your answer, you can add up to 10 vectors, which might not have been obvious. I mean, I might lastly just point that out to you. Right? You can have as many vectors as you want. Just like you can add as many numbers as you want, 5 plus 7 plus 12 plus 35. And they can be minus 16, minus 24, plus 32. And the answer is called the net, right? Same thing with vectors. Even though we do 2 vectors, just to understand the concepts behind it, you could certainly add as many vectors as you want, right? A plus B plus C. What's the resultant look like? There it is. You can have as many as you want. There's no limit to the number of vectors you can put into a vector addition problem, just like there's no limit to the numbers you can put in just a regular addition numerical problem. So for that reason, when you're looking at this calculator, it will take up to 10. The magnitude of A, the first one was 12, I think, right, Matt? Wasn't that your choice? And then the next one was 24. Stop me if I make a mistake, because I'm just going on memory right now. The direction was 45, and then the direction of this one was 300. Can anybody just confirm that looks correct? The first row is vector A, 12 miles in a direction of 45 degrees. The second row is vector B, 24 miles in a direction of 300 degrees. Is that right? Can anybody just say yes if that is right from the original information that was given? All right, let's just calculate and compare it to what we have here. Go back. Oop. If it's not right, then there's a mistake. Let's see. It's not exactly correct. 300, although the angle is 329.05. I wonder why there's a difference in the magnitude by a small amount. I'm not 100% sure. But I do notice the angle is exactly right, 329.02. I have 329.05. That's just a round. Oh, I wonder if it is a rounding. It could be. Yeah. So I haven't thought about that in a while. So just remember that when you plug, if you use a calculator like this, it's giving you the exact answer, meaning every moment there was a calculation that was done, it never rounds. It just keeps the true values like 12 or 3, where I was rounding with decimals. So the advantage is to keep those actual numbers to get the precision exact. You would have to do that. Since I was rounding and I rounded in many places, my exact answer might be slightly rounded. Slightly off, I meant, due to my rounding. So it looks like it's off by 2 miles or so, 3 miles, but the angle is correct. So my point being, that's all correct. Everything I showed you is correct. All those steps are correct. I'm going to give you a problem now, and just know that there's a calculator that you can use to just check how you did. All right. There are no questions. I'm going to erase this. I'm going to write a problem on you. Or actually, you know what? There's already one on Google Classroom, I think. Let me just use that. At least show you where it is. One second. Close. You want to save? No, I don't want to save. So if we go to Google Classroom, this is going to be your homework assignment. This problem that I wrote. So I think it's actually all the way back in the original AP summer Google Classroom for this that we used over the summer. It hasn't been copied and pasted in, but I probably will. At some point today, I'll copy and paste it into your actual one. But just know that if we go back to the original summer one, which is here, and go to the bottom, because it was one of the last things I think I had posted. At least I thought I did. Maybe not. There it is. There it is. So I'm actually going to just copy it right now. I'll just post it right here. So you guys are period 6. So that's your homework. It's similar, very much similar to what we just did. It gives a word problem like this. Jimmy starts out on a hike, walks 6 miles, and so forth. It gives the direction of the first displacement and a distance and direction of the second displacement, 8 miles at 32 degrees. Determine Jimmy's net displacement, which is a vector that points from his original starting position and ends at the end of this 8-mile trip. That would really be in magnitude. It should say determine the magnitude of the net displacement. And then you're also going to, as it's showing here, try to determine the direction and the length. So you still have, I don't know, 6 minutes left. If you want to just take a break, I don't mind that. If you wanted to just start in on it, you can. That is your homework. It'll take a while. Don't kid yourself. It will definitely take a while. Maybe 45 minutes, I think. Maybe 30 minutes. I don't know. I mean, it depends. It all depends. It depends on the student. You know, if you understood the process and you understood, you already were really strong in trig and all that stuff, then you can do it more quickly. I mean, I was doing it, of course, trying to describe it as I went. If you're just doing it, not having to talk to anybody, and you understand the process, you understand the trig pretty well, you could actually do it in probably 15 to 20 minutes. But I don't expect that. This is the first time you're seeing it. It could take longer. It could take 35. It could take 40 minutes. I don't know. Depends on the person. So that's that lesson. And I can say it's in the bag at this point. I won't do that lesson again. I'll always have it on your posted there, this video, so you can see it if you want again. And then when I see you next, we're just diving right into displacement, position. I'm going to talk about acceleration as well in that class. Constant acceleration, remind a lot of you of what that is. Some of the kinematic equations I'm going to throw up on the board and just start getting you thinking about all those things again. when things are vectors, we will look at them as vectors. We'll see how that applies to those sections. That's, I don't know if I just said Wednesday, I meant to say Thursday. I want to see you on Thursday. It's been hard for me to actually distinguish days for some reason the last few days. I don't know what it is. I think last week I thought it was Thursday and it was Wednesday. And now this week I did that already once. I thought today was Monday and it's Tuesday. It's a sign of mental fatigue. Sitting on a computer all day. All right, if you have any questions, I'll lastly say one other thing then, because I still have a few more minutes. I have this book that I'm going to use. It's called TIPERS, TIPERS. I don't know. It's an acronym. It stands for something, teaching introductory physics, something or other. I don't remember. But it's a really good book, and it's pretty much all conceptual, like good, solid conceptual questions. So we're not far from a point where I might start assigning some of those worksheets. They're all in the book, and I even have a whole solution guide, so I don't have to do it. That's like a really solid solution book that shows all the detail of all the questions. Again, there's no computation. It's nothing numeric. They're never asking you to make calculations. It is mathematical when it applies, but it's all deep concepts relating to each topic, and they're challenging. Some of them are really challenging. So I might very well start assigning some of those. I would probably just scan a few and then post them. In fact, I might give you some of those for the weekend. In fact, now that I think about it, there's a whole section in that book on vectors, and I think most of them, since it's a physics application, it's displacement questions. So perhaps maybe even on Thursday, I might give you some of those just to see what those questions are like and assess the deeper level understanding. All right, guys, I'm going to end the class. I am going to post the link. If you want to watch it again, you certainly may. If you have no question, then I hope you enjoy the rest of the day. Again, the assignment, I already talked about it. I will actually be creating an assignment. I always have to do that, right? I have to create the assignment. So I have to go in and create the assignment, which I haven't done. All I physically did was copied and pasted into the stream at this point. So I'll create the assignment, and then whatever work you have, you're going to have to take a photo of it and upload it. And that will be due, since it's homework, on Thursday before class starts, as in photo form. All right, see you guys later. Have a great day.
Thank you.
You're welcome. Bye now.